I'm John Schlesinger. I'm the Chief Enterprise Architect at Temenos, which is the banking software company. So we sell banking software to banks, and we sell the product that manufactures and distributes their product. And this talk today is about why we think banking is moving from needing a single database, as is typically the case today for its core banking, to needing 3 databases. So what's causing us to believe that we're moving from 1 database to 3 is that banking is moving from being monolithic, where the only way you can get to the bank account is through the bank's own channels, to moving to the cloud, and also moving to being open banking, where you can get to the bank through a third party's channels. And that's changing the architecture of banking. So what I'm going to talk about is what banking looks like today, the monolithic view of banking, what banking is going to look like, we think, in the next few years, the modern view, and then take you through why that modern view, in our opinion, needs 3 different kinds of database, not just 1. And of course, one of those 3, we believe, is a database like Yugabyte. So the objective of the talk is to explain why core banking, which is loans, deposits, accounts like current checking accounts, and payments, can no longer run on a single database, and why rather we think you need 3 different database management systems. So first of all, let's look at what banking looks like today, and we'll start by looking at large banks. So the reason we look at large banks separately from smaller banks is that no bank with more than about 100 billion in assets has managed to move off the core banking systems they built in the 60s and 70s. So this is what those systems still look like. So if you bank with a large bank, in the UK, that might be NatWest or Barclays. In the US, that might be JPMC or Wells Fargo. In France, that might be BNP or Société Générale. They all look a bit like this. So transactions come into the online teller system, and each transaction looks at the balance and records the transaction in a log. And at the end of day, the log goes into a batch system that runs overnight. So some of you may remember that NatWest batch system failed about 4 years ago, and it took them 1.5 years to get back onto an even keel after that. The batch rendezvous with the clearing files coming from the payment systems, makes payment decisions, updates the balances with fees and interest, and then the balances go back to start the next day. And that's still the rhythm of large banks today. And the problem with this system is it was basically obsolete in the late 80s when ATMs were nailed to the walls of banks. So that's what a large bank looks like. Smaller banks have a slightly more modern system. So they'll have teller systems, yes, like the big banks. They'll have ATM systems as well, like the big banks. And they'll have added, as the big banks have, an online and mobile channel. So the same stream of transactions. But now they'll come into an experience platform, platforms like Coney that we acquired in Temenos a couple of years ago, or Backbase, or any of the other experience platforms. That will then speak an API to the online part of the core banking service. And then there'll be a separate bulk part that runs on the online platform for doing the close of business and handling the clearing files. So now it stays 24/7, but it's a monolithic system. It's a single front to back piece of software. And this is the model that's becoming obsolete because of open banking. So if we look at open banking, in an open banking world, we still have the channels, which is where the web and mobile apps are. And we still have the core banking services, which we now call manufacturing services. And then we have to fill in the middle, what you might call blank or white, blind spots or white space, with distribution services. So on the left, they are accessed via APIs from the channels. And on the right, they use B2B interfaces to talk to the core banking. And the whole thing is open, so we can have third-party web apps and mobile apps coming into distribution, or distribution speaking to third-party manufacturing. And finally, we can have manufacturing, our core banking services, speaking to other services distribution. So for example, at Temenos, we have a partnership with Salesforce. So Salesforce distribution can come into Temenos manufacturing. So that's what a modern banking value chain architecture looks like. And it's value chain because it's front, middle, back. Front office for distribution, middle and back office for the manufacturing. And this distribution part is white space for the banks, and it's a blind spot. I don't know if you have a banking app on your mobile phone and you have, say, the Amazon app or say the Wise app from TransferWise, then Amazon and Wise remember your activity. Amazon calls it orders, Wise calls it activity. But the banking app doesn't. It forgets the orders because it's not doing this middle part, this distribution service. It's forgetting what you asked it to do. So it's filling in that white space is why we in Temenos changed the brand name of our core banking service from T24 to Infinity for distribution and Transact for manufacturing. So what does it look like when you build out conceptually that kind of an architecture? Well, your apps come into your experience platform, just as in the second diagram about small banks, and that is of course synchronous. And then they go into, those channels go into the distribution services and the reporting services in the front office. But they don't go into the manufacturing services. We don't wire the channels directly into manufacturing. Instead, we use an event-driven architecture to drive the manufacturing services from events. And we can turn these events into data events in near real time. And we can connect the data events to the outside world through data pipelines. And we can connect the business events to the outside world through fulfillment services. So this is what a modern banking architecture looks like, taking into account open banking. So in this architecture, the distribution services could speak to third-party manufacturing services, that's the related parties at the bottom left, and manufacturing services can speak to other distribution services, that's the related parties at the top left. But there are two value chains here. There's the value chain of banking, which is distribution and manufacturing, and the value chain of information, which is data events and reporting services and data pipelines. And everything above the manufacturing is microservice architecture. So the question is, what databases do these services run on, particularly the distribution services, the manufacturing services, and the reporting services? In today's architecture, where you just have the core banking services, they all run on a single site database like Oracle or DB2 or SQL Server, or in the cloud SQL DB. So single site because it only runs in one data center. Yes, it can run active within the data center like Oracle RAC or DB2 Pure, but it can't run active across data centers that are more than 40 kilometers apart. So it's a single site database. And in this architecture running on the cloud, we believe that the distribution services and the manufacturing services need to run on a distributed database so they can run active both across regions and across clouds. So we already have a bank in Hong Kong running our manufacturing services on a distributed database, simultaneously transacting in an Azure data center and an Amazon Web Services data center. So let's go through the characteristics of those three kinds of database. So the first one is the front office record keeping database. We call this record keeping because we're using the command query separation architecture, CQRS. So that's called command query responsibility separation. Right. So the commands, which are posts or puts, go to the record keeping service for any capability, but the queries, which are gets, go to the reporting service. It can be the same web app, so it's not two web apps, one web app, but we direct the posts to the record keeping and the command and the queries to the reporting. And the reason for that is scale. If you have a teller doing the operations, or in travel, a travel agent doing the operations, or in other industries, some clerical worker taking the orders, then typically they'll do 5 looks, 5 quick gets for one update, for one post or put. So Sabre, when it was running with travel agents, was architected for what they call the look-to-book ratio of 5:1, Sabre being the global distribution system provided by American Airlines. When the travel agents got replaced with booking engines like Travelocity, Orbitz, and Skyscanner, that ratio went from 5:1 to 1,000:1. So the 4 large global distribution systems in travel, so that's Sabre, Amadeus, Galileo, and WorldSpan, all moved to a CQRS model in order to scale. And as banking moves from tellers doing the transactions to the public doing the transactions, we're having to do the same thing. We're moving to CQRS. So we have a separate reporting service for the gets with a separate database. So the front office record keeping database is a distributed database. It's for puts and posts only, but crucially, it's an eventually consistent database. And the reason for that is it needs to be low latency, so we can't wait for commits to come from other data centers, and it needs to be high availability. So if there's a partition in the network, we don't want to lose availability of any one of these services. And in fact, it doesn't matter. So if you're looking to buy a fur coat in New York at the same time as somebody else is looking to buy a fur coat in Amsterdam, if there's only one fur coat left in the distribution center, and you both try to order that fur coat, if you're not partitioned, you'll both see that there's one, and one of you will win and one of you will lose. If there is a partition, you'll both win, you'll both be able to place the order for that one fur coat, but one of you will be told later on, I'm sorry, that fur coat has now gone out of stock and we put you on back order. So it's completely safe to have the front office taking orders to run eventually consistent. And it actually improves the front office because it means you get better latency and better availability. For the front office reporting, we don't need this to be a distributed database because the data events, running on a product like Kafka or Pulsar, do the distribution for us, right? What's important is it's optimized for insert and query. So insert means we need to be able to take thousands of inserts a second and have them added to the indexes in real time. And query means being able to do end user query against that database, lots and lots of concurrent queries, some of them very complex SQL queries at the same time. And crucially, we need to be able to aggregate on the fly. That's because if you aggregate these databases in the database themselves, then late arriving transactions cause you a great deal of problem. But in modern technology, aggregation on the fly is possible with column store. And this, remember, is the target for the gets of CQRS and for the analytics going across the other services. So finally, we come to the manufacturing database, so the database for middle and back office. This needs to be optimized for high throughput. It needs to run at very high scale and at very low cost. It needs to be strongly consistent because we're moving money from one data center to another, from one account to another, either doing internal transfers, which may be between data centers or regions, and doing payments, which is almost always going to be across data centers, going from one bank to another through a clearing and settlement mechanism. We want it to be active-active, so that if there's a failure of a data center, we can seamlessly go to another. But we don't mind if it's more latent, because remember, as I said at the beginning, the channels are not directly connected to this service. The service talks events, distribution sends events to this service. So if it goes down, is unavailable for a minute, actually the channels aren't going to notice. And the event system will just start routing events to the other data center. So we can sacrifice latency and we can sacrifice availability in order to get that strong consistency with cross-region, cross-cloud, active-active work. And again, because the channels don't connect to this, and nor does the reporting, It's post and put only. It's only for updates and inserts and deletes. It's not for reads. And this is where a database like Yugabyte plays in our architecture. In particular, we really need databases that are auto-sharded. This manufacturing tends to be global, whereas distribution tends to be regional. So there's natural sharding key for regional, which is the geography. There's no natural sharding key for manufacturing. And therefore, the Yugabyte auto-sharding is a crucial feature for us. And the fact that it runs as strongly consistent as a distributed database, both across region and across clouds. So this is where Yugabyte plays for us. So this architecture that I've just described has three different kinds of database. It has the front office record keeping database that's eventually consistent, optimized for puts and posts, and provides low latency and high availability to support channels. The front office reporting database that is optimized for insert query, it takes the gets from the CQRS services, and it also offers a GraphQL interface for analytics. And it runs on a column store database so that we can do aggregation on the fly, and is not necessarily distributed because we can use the data event distribution instead. And then finally, the manufacturing database, which is strongly consistent, optimized for throughput, and where we sacrifice latency and availability in order to have strong consistency. And this is where Yugabyte plays. So I started off by talking about how banking is moving from a monolithic architecture in banking and a monolithic architecture in the software to support it into a more distributed architecture to support open banking and indeed the move to the cloud. And in this new architecture, we believe in Temenos that you need at least three different kinds of database. Eventually consistent database for the front office for record keeping services, a column store database optimized for insert query for the reporting, and then in the manufacturing, where core banking plays today, moving off a single site database onto a strongly consistent distributed database optimized for throughput, sacrificing latency and availability. And that's where we think Yugabyte plays in this modern architecture. Okay, thank you very much. And then we'll leave time now for Q&A.